Yeah, today in this lecture, so we'll discuss about Petri nets. Okay, so it's a model oriented specification technique. So usually Petri nets are used to model concurrent systems, as we already discussed when I was talking about property oriented and model oriented specification. So, so prettinets are used to model the functionality or behavior of the system. So usually, uh, so we use prettinets to model the functionality or any of the behavior of any concurrent system. Okay. So Petrinet is a formal language or graphical language for modeling the system with concurrency. Okay. So as I told you before, okay. So this is also a language and this is a graphical language as well, which is usually used to model the system with concurrency. Okay. Wherever multiple different processes are going to run at the same time. Okay, so if that sort of requirements are there, then usually we are going to use paternets to model that. Okay, so paternets is a bipartite graph. Usually we'll see in the next slide. So usually it contains certain number of nodes. Okay, because it's a graphical language, so you will see some sort of edges, nodes. Okay, it is what exactly represented using a graph, represented as a graph, and it is a bipartite graph. Why it is a bipartite graph? We will talk about that. But as of now, so usually two types of nodes. Okay, so one is a place or the condition. Okay, so usually that holds some number of tokens. So you will understand why each and every place should hold a token maybe in the next slide. Okay, so as of now you can think of place is something like a event. Okay, sorry, place is like something like a entity. Okay, or within that particular entity certain conditions need to be met. Okay, if those conditions are met, then some processing will be carried out. Okay, some processing will be carried out, and the processings or the functions will be represented through the transitions. Okay, so unless or until some conditions are met, the processings will not be carried out. Okay, so usually, so I said you, so every system will have some sort of it should have some sort of data which will be given as input to the system, right? And some conditions need to be met so as to if those conditions are met, then usually the processing will be carried out, right? So that is what exactly we try to model. Okay, that's the way that we model the behavior of the system, right? So usually here you will have places. I mean, some nodes as a place, some place nodes, and some will be of transitions. Okay, so usually these transitions will represent some event or activity. That means some processing. Okay, so right, and tokens are circulated among the places. Now, so very at the if the maybe in the at the initial state. Okay, so maybe so the places will carry some will have some number of tokens. After that, these tokens will be circulated, okay, among different places, and we'll see that in the next slide how it is a why it is a bipartite graph, and what is a place, what is a transition, okay, and what are the tokens. Now we'll see, right? So places and transitions are connected by directed arcs. Okay, so usually, so these places, as I said you, there are some places and there are some transitions. So these places are also nodes as well as the transitions are also nodes. Okay, so now these, I mean, place and transition, they both are connected by a directed arc. Okay, place and transition are connected, they are connected by a directed arcs. So arc only exists between transition and place, and vice versa. That means so there will be arc only between transition and place or place to transition. Okay, but there will not have any there will not have any arc between places or between transitions. That is what you need to understand. Okay, so that is the reason why it is a bipartite graph. Okay, so whenever you have something like this, okay, you have some disjoint sets. If these two disjoint sets are connected through arcs, okay, but that is what exactly a bipartite graph, right? So that means it is something like this. So you have places is one disjoint set, transitions maybe the other disjoint set. Okay, now so you will not have any arcs between places, or you will not have any arcs between transitions, right? So you will also always have something like this: places to transition and transition to places. Okay, so these sort of things, or places to transition and transition to places. So place, transition, place, this sort of, wherever you find this sort of pattern, that is what exactly a bipartite graph is all about, right? So it is something like this, like, okay, so here we represent the transition by a vertical line, or you can have a, maybe you can have a rectangle here, okay, instead of a vertical line, or you can have a box, okay, or you can have a square box, or you can have a rectangle box, anything like. So this is also considered as one node, okay, and the circles are representing places, and this vertical line represents the transitions. Okay, so now you can see, so you do not have a directly edge between place to place, okay, or place to place. You do not have a direct edge arc. Okay, you will always have something like this. So place to transition and transition to place. That is the reason why it is a bipartite graph. Okay, this is a bipartite graph. Okay, so if you right, so can anyone tell me what is a bipartite graph? Anyone knows?
Yes, sir. Yes, sir.
What is that?
A bipartite graph is divided into two parts, in which each every node is in divided into two parts, sir. One node is in one part and another node is in other parts. It's like that, sir.
No, what's the interesting part of it? Okay, bipartite graph.
Sir,
Nodes
it
are
elements of one
nodes are not connected and they're connected by
Even
element
nodes of one.
chromatic lines too.
Yeah, can you please talk one by one? Okay,
It's too
Pavitra.
colorable.
It's
Yes, yes, yeah. Okay, Aparajita, you say what is it?
yes, sir.
So I asked Aparajita because he raised a hand. Okay, so I asked. Aparajita. Okay, so now, yeah, Aditya Singh, you answer. What is
Yes,
a
yes, sir.
hmm,
Sir, a bipartite graph
So
is a
am
graph
I
in which
allowed to
vertices can be divided into
apply?
disjoint or independent sets, and
okay,
such that every edge connects a vertex U, matlab in two sets of U and V,
okay,
and
right.
every okay, and
So,
every
so,
edge.
so you do not have any ads among the sets. Okay, you do
Yes,
not have any ads among the sets. Okay, so that is what. So the graph representing two disjoint sets. Okay, I mean disjoint set of vertices. Where these within a set they do not have any edges, but so you will have edges between those two sets. Okay, I mean vertices of those sets, right? So that is what exactly a bipartite graph is all about, right? So similarly you can see now if these circles are one disjoint set, and at the vertical ones the transitions are maybe another set. So then you do find edge always. Okay, that is why. So this is a bipartite graph. Okay. Now, as I told you, so each and every entity or the place will have some number of tokens. So you can see here there is one token in the the lower place contains two tokens. Okay, so there are certain number of tokens available, right? Tokens means you can think of something like this. So it has some data. Okay, so right, unless or until it has some data for processing, so you are not allowed to fire the transitions. Okay, you are not allowed to fire the transitions. Okay, so I mean each and every entity or the place should have some data before processing. That is what we say. Okay, so it can be represented through a concept called tokens. Okay, so tokens can be can be thought of a data. Okay, or it can be thought of as some sort of resource. Okay, so if those are there available with the entity, now it can fire a transition. Transition means it can do certain processings. Okay, if it has no data, that means it is not allowed to do fire. Okay, so you can think of something like this. Okay, as of now you can understand. So each and every so the input places will have some tokens, then only it can fire a transition. It can fire a transition, otherwise it cannot fire a transition. So this is what. So now after firing the transition, so some of this a token will be removed from the input places and it will be added into the output places. Okay, this is the way that we will carry out the whole I mean the petrinets actually works in this way. Okay, so we'll explain maybe I'll explain certain things, certain basic concepts. Okay, through examples, then you will be able to understand. Okay, as of now you understand. So it requires certain number of tokens in the input places. Okay, so input places means these are the places connected to a particular transition. Okay, for this transition there are two input places. Okay, so if the transition to fire only if the input places contain some tokens. Okay, if the input places have no tokens, then the transition cannot be fired. Okay, this is the way that you can think of. Now once the transition is fired, then that means now we are moving into, I mean we are going to some sort of output places. Okay, so that means it is giving some sort of output. Okay, so the output alternatives can be of two here. Okay, any doubts so far? Okay, so transition is triggered only when at least one token is present in all input places. That is what I said you before also. Okay, so the input places of a particular transition should have at least one token, then only that transition can be fired. Okay, yes, yes, someone is going to ask.
So
Yes,
where
yes.
are like how do we get the tokens? Like, is it from programming language? Like, what type of
Yes,
tokens?
it is, it's our specifications. Okay, so it is what we say. As I said, if let's say there are in a particular in a particular system. Okay, so you may have certain number of entities, and these entities are carrying out certain activities. Okay, so now what I say is, unless or until some data is there with that particular entity. Okay, so it cannot process. Okay, yes or no? Like you can think of let's say you wanted to model a printer. Okay, you wanted to model a printer. Okay, now unless or until a print command is given by you and it is in the queue. Okay, that print whatever the printing request that you have given, that should be there in the queue. Okay, if there is no printing request in the queue, that means your printer is not going to print. Yes or no? So that means there is some sort of input condition, right? So at least in the system there should be at least one request, okay, for printing. If there is no request, so the printer is not going to print, right? So you can think of like this. So here also we are going to model the behavior of the system, right? So that means, so whenever you wanted to process anything, so first thing is that you need to have some input, right? So if that input is not there, so usually I think we should not process. Okay, so this is what the idea, right? So now this can be modeled by a concept called token. Usually we say token. Okay, so if there is two requests, that means there should be two tokens. Okay, you can think of like this. Okay, so if there are two tokens in the system, that means this, yes, Saket,
Sir,
Saket,
yes, sir.
you going to ask something?
No, sir.
Yeah, then you mute. Okay. Okay, anyone else want to ask something here, or is it clear
Yes,
to
sir,
you?
I had a doubt.
Yeah, ask me.
So, you said about Petri
Yes.
bipartite graph. So, I am asking what is the function of transition, because in bipartite graph there is nothing such as transition function. So, what is the
No, no,
transition in Petri?
no. You see, you understand graph. What is a graph?
So, a graph is a collection of edges and vertices.
Connection of edges and vertices.
Collection
No,
of collection.
no. So graph consists of certain number of vertices, and these vertices are connected by a
Edges.
edge. Okay, right? That means so that these vertices are connected through each other, right? Now you see, so I said you here the circles represent vertices as well as the vertical line. Okay, that's a transition. This is also a node. Okay, it is also a vertex. Okay, vertex. This is also a vertex. So now your input place vertex is connected to transition vertex. Okay, so now you think of, there are two disjoint sets. Okay, one disjoint set contains input places, the other disjoint sets contains transitions. Okay, and if you have edges between them, okay, you have edges between them. Now if that is there, then it is called as a graph, a bipartite graph. Now our Petri net also have the similar property. Okay, so you have some vertices, okay, and these vertices are connected to the transitions, not to the places. Okay, let's say let's say in our graph, if you do not have these transitions, okay, then what will happen? Then what will happen? Now these vertices are connected to each other, maybe. Okay, if we say, so these circles are part of one disjoint set, then what will happen? So then we can say that it is not a bipartite graph. When you can say bipartite graph, there are two different disjoint sets, okay, and these two disjoint sets are connected, okay, by an edge. Then it is a bipartite graph. So our pretty concept also similar to a bipartite graph. Okay, this is what I say, but it is not saying that it's a bipartite graph. Everything like tokens are not usually there in bipartite graph. Okay, you will not see any bipartite graph. So it's a concept. The concept is so very similar to bipartite graph. Okay, do you understand
Sir,
now? Yes.
yes. Sir, suppose there is n number of input places, no? Means number of places in side of input places like n input places. So the token should be at least one in all places, at least one.
Yes. Yes, at least one in all of the input places. Then only that particular transition will fire. Okay, so that is the condition. Okay, so let's say if you have only one input place to a transition, so in that case only you need one token in that particular input place. Okay.
Okay, okay, sir.
So in all of
And
the
the transition is something like the processing system, where the
what?
processing is the transition.
Yes, that is what I am saying, right? So transition is like a processing, and so to that processing, certain number of entities, or you can say any sort of any object, or whatever may be, or any input system you can think of, right? So that is acts as a input system, right? So that means so that particular entity should have some tokens. Okay, then only the associated transition will be fired. Okay, so this is one condition. Okay, so I said you, so for a particular transition, all input places should have at least one token, then only that transition will be fired, otherwise it will not fire. Okay, this is so once fired, one token is removed from all input places and added to all of its output places. Okay, so that means once the transition is fired, then what will happen? Now from all the input places, one token will be removed and it will be added to the output places. Now let's say, for example, this transition is fired in this case. So what will happen? Now the from all input places, one token will be removed. Then what will happen? So first input place will become 0, no tokens, and the second input place will have one token, and in output places you will have 1 1. Okay, the output places you will have 1 1. Okay, do understand? So that this is the way that when the transition is fired. Okay. Now I just explain this thing. I mean, this is what I wanted to explain. Okay, so now let's say, for example, here is a transition T1. Okay, and for this transition T1, the input place is P1 and the output place is P2. Okay, so before firing, let's say before firing, this input place 1 carries one token, has one token. Okay, so there is a condition like this, unless or until it has one token, so T1 cannot be fired. Okay, so after firing T1, what will happen? Now the token from this input place is removed and the token will be added to the output place. Okay, so that means now this input place now cannot fire a transition T1 because it has no token. Okay, so that means now this P2 has a token. Okay, if this P2 is further connected to some other transitions, now that transition will be fired. Okay, do you understand? Any doubt so far?
Sir, if an input state has two tokens, so one by one the tokens will be moved to output, right? Or
Right.
how?
One by one. Okay. So
Okay, so for example, the first token moved from input through the transition, then it went to the output. Then what about that? Then what about the first token after the second token starts its processing? Means after it has reached to the output, first input token, where did it go? Means
now that is what I said you very beginning. Now these tokens are actually going to circulate among different places. Okay.
okay.
So they are going to circulate within the system, and this way we're going to study the whole system, right? So because transitions means what? So there are different processing. Now we are going to see how these processings are carried out parallelly. Okay, and at any point of time, So how many number of, you can see, and how many number of such actions are actually executed. Okay, whether the system is going into any sort of deadlock situation or not, there will be going to study. So basically now you understand something like this. Okay, I will be going to some example, then you will be able to understand actually whole about patronage, right? As of now you understand. So something should be fired, that means the transition T1, if the transition T1 should be fired only when the input place P1 should have a token. Okay, once the T1 is fired, once the T1 is fired, that means the processing is carried out. Now the token will be added onto the output place. Okay, so before firing T1, so the token with P1. After firing T1, the token is with P2. Now you can think of, okay, this is the way that it carries. Okay, now we'll see in the next slide. So these patronage actually can be formulated this way. Okay, so it has these 4 different symbols. You can see it's a so it's a tuple of 4 attributes you can think of, right? So here P, T, I, O. Okay, so P represents the number of places in the graph. Okay, so P represents the number of places. Okay, T represents the number of transitions. Okay, now I and O are the matrices showing input places and output places for the transitions. Okay, so like you can think of, okay, you draw a matrix. Okay, you draw a matrix. Maybe it's a n by n matrix. Okay, m by n matrix. Okay, you can have in the in the row wise you can have places, and in the column wise you can have transitions. Now you can say, so for a particular transition, okay, so which one places are the inputs? Okay, input places. Okay, do you understand? So can you tell me, so the graph, if you want to represent this sort of thing, right? Which are the places will be the input places for a particular transition? Okay, if you want to represent using a matrix, how that matrix will look like? Can anyone tell me? Anyone guess how it looks like?
Sir, it's a 2D matrix.
Okay, 2D matrix, and the contents will be in what form?
Sir, the transaction
Zero and one.
and the rows are of places.
Eh? The values in a matrix
0
will
and
be
1 we can play.
0 and
what?
1, sir.
Yes, 0 and 1. Okay, so this way you can say, like you can see, so P1, P2, P2, so on, PM, maybe the column wise you can place so you can have a matrix of m by n. That means you have P1, P2 in the row wise, and column wise you can have T1, T2. Now you can find like this for a particular transition T1, which are the ones, which one are the input places. Okay, so whichever the ones the input places, that will be marked as 1. If it is not the input place, then marked as a 0, right? So usually you will get a matrix, and that matrix contains so zeros and ones, okay, through which you can say, so it's a adjacency matrix kind of thing. Okay, so for P1, okay, so who are the adjacent transitions, you can say like this. Okay, so that can be marked. Similarly, for the output also you can mention. So input and output are the different 2 matrices. Okay, and there is a marking of a patronate at any point of time. Okay, so the places contains what number of tokens. Okay, so at any point of time, these places contain some few number of tokens, right? Now that instance is called as a marking. Okay, so let's say you have a graph. So in this point of time, let's say I go back to the previous, can you tell me what would be the marking for this? So we have two places, okay, place 1 and place 2 in this graph. Okay, so what is the marking for this at time t0, let's say at time t1, okay, or at time t0, what is the marking?
For
1 0.
P1 it's 1 and for P2 it's 0.
Yes, the
1
marking
0.
here is 1.
Before firing T1 means.
No,
Yes.
before, after, yes. So like this, okay, before firing t1, so the marking is like this, 1 and 0. Okay, input place P1 has 1 and P2 has 0 token. Now after firing T1, so P1 has 0 and P2 has 1. So this is what we call as a marking. So at any point of time, so recording the number of tokens carried by each and every places. Okay, so this is what we call as marking, right? So now you will have, now in this case at time t0 you have one marking, at time t1 you have another marking. Okay, so like this. So usually whenever you say any pattern net, so usually so you will have a sequence and then you will have a marking. Okay, now so here you can understand, right, mi of t, that means at time t, okay, the marking, that means the number of tokens in place I at time t. Okay, so the number of tokens in place I at time t. Okay, and m of t0 is the initial marking of the system. Okay, so that means initially whenever you are going to start the system, so you will have some marking. Okay, after some time the marking will be converging to some number, right? So initially maybe you can see, so in this previous diagram, right, maybe the so our start so initially we start with the marking 1 and 0. Okay, now after some time the marking is changed to 0 and 1. Okay, so now this is a very simple system, right, where there is only there is only one processing required and one input place and one output, right? Now you can have a system where you will have many such input places and you will have many more transitions. Okay, so that is what we are going to study, right? In a large system you will have many more processings and this processing will be carried out parallelly. Okay, that is what in the concurrent systems we are going to study. So these are the basics of this pattern net, right, we are talking now. So now coming to a very maybe you can think of some circular system. Okay, so now you can think of something like this. Okay, so how these different processings are executed sequentially. So as I told you, the initial marking of this system is something like this. Okay, what is that initial marking? 1 0 0, because the P1 contains, the input place P1 contains 1 and P2 and P3 contain 0 0. So this is the initial system. So initially the system starts from here. Okay, so I told you unless or until T1 system, I mean T1 unless or until so the input places to this T1 transition has at least one token, this will not fire. Okay, now this input place has one token, because it has one token, now this T1 will be fired. Okay, so that means this transition is carried fast. Okay, and after that what will happen at T1 time, what will happen? Now this token is removed. Okay, and this will be added to the output place. That means the token is moved to P2 place. Okay, now because the input place of this T2 transition has a token, now this transaction will be fired. Okay, this will be fired, right? Now what will happen? Now the token, whatever it will be contained in the P2, that will be removed and it will be added to P3. Okay, now thereafter what will happen? now because for the T3 transition, so this P3 has a token, right? So now this T3 will be fired, and after that what will happen? Again the token will be coming back to the input place P1. Okay, so now you can see, so it is something like a time sharing system. Okay, you are going to develop a time sharing system or a round robin system. Like, you know, what you are doing is now these actions are carried out sequentially. First T1 is fired, then T2 is fired, then T3 is fired, and then T1 is fired. Okay, so that means some of these processings are carried out in a round robin fashion. Okay, now this sort of system is actually we are going to model, right? So by using patterns, right? So because now here you can see, so there are many number of processings. Okay, but these processings are carried out one after the other. Now this is something like a very much like a round robin system or a sequential processing. Okay, but we'll see the complex ones hereafter. Okay, so now the sequential actions are carried out this way, right? So initially, one of these input place will have a token, then only the action will be fired. Okay, or the transition will be triggered, and thereafter the output place will contain a token, after which the next transition will be fired. So keep on, right? This is a very sequential action, right? This is what we have seen in the previously. Okay, now we can model dependencies also, right? We can model dependencies. How we can model a dependency? So it is very similar to something like this. As I told you, right? For all the input places, okay, for all the input places of a particular transition, okay, all the input places of a transition should have at least one token. Should have at least one token. Okay, if that has no token, that means the transition will not be fired. Now you can see in this case what is happening. Will this transition will be fired? Will this transition will be fired? No. Why it cannot be fired, or why it is not fired? Because one of the input place has no token. That means, so this process is waiting. I mean, unless or until this input place gets a token, so this transition cannot be fired. That means you see dependencies, right? So that means these both input places should have tokens. Okay, that means one is dependent on other also, right? Unless or until, so both have both have tokens, so this transition cannot be fired. Okay, so now you can understand. So it is something like a and or operation kind of. Okay, so unless or until meet these two things, so you cannot fire. Okay, this is something like a dependency. Okay, so the dependency can be modeled this way. Okay, any doubts so far?
No, sir.
Okay, okay. So now we can see there is a situation where you can have some sort of conflict. Okay, so now what is a conflict that you will try to understand, right? So now you can see here. So let's say there are two transitions. Okay, there are two transitions you can see in this graph. Okay, so for the first transition, so you have a P1 and P2 as input places. For the second transition, you have P2 and P3. Now here you can see the input place P2 is common for both the transitions. Now the transition T1 and transition T2. Okay. Now what we say, let's say the first one is a T1 transition and second one is the T2 transition. Okay. In order to fire this T1 transition, so what we need? We need tokens at P1 and P2. Okay, if we have tokens at P1 and P2, then only you can fire that T1. Okay, right. If we have tokens at P2 and P3, but not at P1, then we can fire T2. Okay. Now, what will happen if we have, if we have, if we have tokens in all of these 3 input places, then what will happen? Now there will be a conflict. Now there will be a conflict. If all of these input places have tokens, then there will be a conflict. How it is a conflict? Now I said you, so I said you, if the if you want to fire the T1 transition, you need to have P1 and P2. Okay, these entities should have tokens, right? Now, so I mean here you have an input place which is actually a common for both of them, right? Both of these transitions. Okay, do you understand? Now you can think of, let's say here is a system. Okay, here is a system or a process. Okay, can it concurrently work for 2 transitions? No, it cannot. So that means you need to have some sort of policies you need to define. Then if there is this sort of conflicts are there, so in that case what you need to do is you need to decide. You can say either first this will be allowed, T1 is allowed, or maybe T2 is allowed first. So you need to decide some sort of policies, and through those policies you can decide who should get I mean which one of the transitions should first get filed. Okay, so that can be defined by some sort of policy, but you can understand here is there is a conflict. Okay, because so so two things cannot be filed. Let's say for example, if we do not have a common one here, so do you find any problem? Let's say P1 P2 here, and there is a P3 P4. Now P3 is connected to T2 transition, and P4 is connected to T2 transition. P1 and P2 are connected to transition T1. In that case, you will not have any problem because these entities are allowed to do the processing. Okay, do you understand? Any doubts so far?
No, sir.
Okay. Now you see how you can model a concurrency, right? So how you can model a concurrency, that we will see now. Let's say, as I said you, so what? So if the input place to this transition, okay, the first transition, okay, if there is a token here, okay, so what will happen? Unless or until there is a token in the input place for this transition, first transition, okay, so it cannot fire, right? So let's say you assume that there is a token, okay, in the input place. What will happen? Now this transition is fired, the first transition is fired, and that means the input the token from the input place will be removed, and it will be added, or it will be added onto the output places. Now what will happen? The output places will have, each one will have token, okay, one, so that is removed from the input place and it is added to the output places, right? So each output places will have one. Now what will happen? So now here you can see, so this input place, because the output place has a token, now it can fire the transition here, the upper transition can fire the same time. So the lower transition is also getting fired. Okay, now once after firing, right, now in its output places, so you will have tokens, right? Now what is saying? So unless or until for the last transition, that means the fourth transition, so the input places should have some tokens. That means what we are doing, so we concurrently execute 2 different processes here. You can see, you can think of, okay. So this way you can settle, right? Because here you have, in the fourth transition, you have a dependency. That means unless or until both have tokens, that means both have completed their, maybe they have input data, then only the transition will be fired. Okay, that means they are going to a output state. You can think of. Okay. So this is the way that you can think of. Now you can model any pattern net, right? Any doubt here, Rohit? Yes, you are going to ask something.
Sir.
Yes.
So at the time now when the all transistors are fired,
Huh.
so in last nodes, there is two tokens. There will be
Where?
two in
Which one?
last node, no?
Last transition. Okay.
Yes, sir. After
So
completing the transaction 4, there will be two tokens.
no, there will be only one token. So there
So
will be
because
only
there will be the two input places na, and one output places.
no.
Okay.
One token will be removed from each one of the whenever there is a transition fired. Okay, one token will be removed from each of the input places, and one token will be added to the output place. That is what we do. Okay.
So that what I am saying that there is two
No, it
input
is
places,
not
na?
like this. It is not like this. Okay.
Okay.
So for for a particular transition, if you have two input places,
Yes.
so two tokens will be I mean
One removed.
two tokens are actually removed. Okay. Yes.
Yes, sir.
So
Yes.
then you have to add two tokens in the output place. It is not like that. Okay.
Okay.
So what it is, what it all tells you is, so whenever a transition is fired, the one token from these input places will be removed and one will be added to the output place. That means, so you have enough operations carried out, whatever the data is really required. So that is, now you can see here is also you can think of, let's say in the first transition case, you have only one input place. Okay.
Okay.
One input place, but you are placing in the output places two tokens. So it does again, that's a problem. Otherwise, the way you are thinking, right? It is not like that. Okay.
Means
So
we are removing one tokens and we are adding one tokens on output places. We don't bother that how many output places are there.
right. That means we are allowing, right? Okay. Now you see the output places after the first transition occur. So each of the output places will have token. As a result, what is happening? So they can carry out parallelly their actions. I mean the T2 and T3, sort of transition, they can carry out parallelly, right? After completion of T2 and T3, now again T4 is executed. That means what you try to do, some parallel processing can be carried out in between the system, right? Okay. So let's say you going to, you doing certain processings. So this processing requires 4 steps. Okay. 1, 2, 3, 4. Now what you are saying is, so now processing 2 and 3, so they can be parallelly executed. Okay. So after the processing, the T1 is carried out. Now 2 and 3 can be parallelly done. And once they completed their activity, now the 4 can be carried out. This is what exactly we are going to say. So this is what a concurrency is all about, right? So this is what model through patronets. So any doubt so far? Right. So now, yes, ask me quickly. Yes.
Sir, for the first step, we have one input symbol. So one input will be removed and added to one output symbol. Then what
Right.
about the second output symbol? Means again we will have another input symbol added, and again we will have removed it from the input and added to the output like that.
Right. So that means what you are doing
So at a
when,
time only one operation will be performed, right? Not concurrently.
but concurrently will be done. You
Okay.
see,
Yes.
do you understand? So whenever I say, in an input place, if there is a token, then only the transition will be fired. Okay. Now,
Yes.
for the first transition, so there are two output places, right? And these two output
Yes.
places have tokens now, right? As a result, what
Yes.
will happen? T2 and T3 can be parallelly executed, right? These transitions can
Yes.
be parallelly done. Okay. After their completion, now what will happen after the T2 and T3 fight? Again, the token will be coming to the output places, right?
Yes.
Now, these two output places of T2 and T3, so they have tokens. As a result, what will happen? Now T4 will be executed. Okay.
Yeah.
Yeah. So that means, so as I told you, so if there are various tasks, okay, now you can out of this T1, T2, T3, T4. So here exactly T2 and T3, so they can be parallelly executed. Okay, this sort of things. Now you can understand now how we are going to model this whole system behavior, right? So any system can have this sort of task. Now we try to model, let's say, resource sharing. Okay, we can think of something like this. Okay, so take an example of resource sharing, right? So we see oftenly this thing in operating systems, right? So resource sharing, right? You have, let's say, here you have two processes. Okay, so the first sequence of transitions, so that are belonging to a process one, and the lower the lower sequence of transitions, so that belong to process 2, let's say. Okay, and you have a resource at the in between. Okay, that the center one. Okay, that is a resource. Okay, you have. So now what I say here in this case, now, so our initial system looks like this. So initial system here is something like this. Okay, so we give permission to the process P1. Okay, because this process P1 has a token. Okay, and it has a resource. Okay, when it has a resource, what it can do, now this transition will be fired. The upper T1 transition can be fired. Okay, right? So then what will happen? A token is going to come to the next next node. Okay, so maybe to the output place. As a result, what will happen? So now the token that is removed from here, okay, right, the token that will be removed from here, and then so in the output place, that means the above that, in the first process. Okay, so the first row represent process 1 and second row represent process 2. Okay, what we are saying is, now you can think of, so we are talking about the process 1's first transition. So now if this is triggered, what will happen? So output place of T1 will contain a token. Okay, will contain a token, right? Now when it has a token, okay, now the T2 transition will be fired. That means, so by taking this resource, the process P1 is carried out certain activities. Okay, I mean some activities or action or the event is carried out. After that, what will happen? A token will be added to its output places. Okay, now what will happen? So that token is added to its two output places, right? So as a result, again the center one, again it gets a token. Okay, back.
Hello.
Yes.
Hello, sir. Sorry to disturb you, but our other class has already started. It's
Okay.
overlapping.
Okay, so fine. So I about to stop this. Okay, so it is almost done. So you can understand, right? So what is happening here is the resource is taken and utilized, and certain processing is carried out. Now this is the way that you can think of. Once the token is coming to the resource place, now this can be as a input to the process P2's T1 action, the below one. Okay, that is the input, right? Unless or until a token is there with the P2 processes input places, so now that transition will not be carried out. Now you can think of, right? So this is the way that you can allocate the resources to different processes. Okay, clear? Any doubts so far? Is it clear?
Yes,
Yes,
sir.
sir.
Okay, so even if it is not clear, you just let me know that, so maybe I can continue this resource sharing part in the next lecture again. Okay, now I stop the recording. Okay, I stop the recording.
Sir, when is the next class for this week?